Hello, and welcome to another edition of Asynchronous Calculus brought to you by Ms. Bowman. We are here to go over the Unit 2 Day 4 notes in case you missed class today, or in case you couldn't make it, or just in case you want to hear it again because you didn't understand it the first time. If that's the case, make sure you're skipping through. Again, if this is your first time, I'm going to tell you to pause, unpause. I'll probably ramble, talk to myself a little bit, talk to you a little bit, and we're going to get through this lesson. Okay, so today we're going to be introducing the idea of the second derivative. Excuse me, sorry. I always have to cough when I'm recording these. But we're going to draw conclusions about the second derivative. So today we're going to talk about what is the second derivative? What do you mean? There's more derivatives than just the derivative. So we're going to talk about what it is, what it means, what it tells us about a function, and what it tells us about the derivative. And likewise, we're going to be able to, based off a function or a derivative, tell us things about the second derivative. So kind of where does the second derivative play in and that kind of stuff. So to get your brain going, I want you to think about, what do derivatives tell us? So derivatives are what we've been studying so far in this unit. We know we denote it as f prime of x, or f prime, or dy dx, df dx, all those names of the derivative. Okay, so I just like to go through those names over and over and over again. And what does the derivative tell us? Well, it gives us the instantaneous rate of change at points for a function f of x. Okay, it gives us the slope of each of those points. And in a situation, what that does is it tells us what the rate of change of a function is, or how a function is changing. Well, what would the second derivative be? I'll give you a hint. It's the derivative of, you guessed it, the derivative. So if the first, what we call the first derivative, gives us slopes of f of x, the second derivative gives us slopes of f prime of x. It gives us the rate of change of the rate of change. In other words, it's going to describe how the slope is changing. Okay. We know not all functions have the same slope. So for instance, if I were going to be looking at this, if you had to describe the slope for each of these functions, that's the same graph again. I did not. So the slope of all three of these functions. You could say that the slope of all three of those graphs is positive. They all the points have positive slopes. So f prime of x would be positive on all three of those pictures. But if you look at them, they are different. So because the slope of each one is not the same between them, the slopes are different. If we look at these points right here, all the slopes are the same because it's a linear function. So if this line has a slope of 2, every point on this line has a slope of 2. This function, if I look at these points, you can see that the slopes are different. The steepnesses are changing, okay, of each of these. So the rate of change, or the slopes, are actually changing themselves. And that is what the second derivative is going to describe. It describes how the slope is changing. It's the slope of the slopes. Okay, to write the second derivative, if we're using prime notation, if I want to say second derivative, just to kind of like let you know, I'm just going to use 2 tick marks. And how I would say that is I would say that as f double prime. Okay, same if I was using y, it would just be y double prime. Now, if we're using the Leibniz notation, it gets a little tricky. So if I do dy dx to denote the second derivative, I'm going to say d squared y over dx squared. Now, a lot of students are like, whoa, Ms. Bowman, why is the squared in different place? Well, the second derivative is taking the derivative or finding the derivative of the derivative. So if you think about the command form of the derivative, this is saying find the derivative of the derivative. The derivative of the derivative is the second derivative. Now, if we look at this notation to kind of describe it, if you look at top, there's two d's. That's why it ends up being d squared. And there's two dx's. So instead of putting it in parentheses, they just say dx squared. Okay, so that Leibniz is the second derivative notation. If you're comfortable with the double prime, we're going to use double prime. So let's go back to my example of how we can say that the slopes here are different. If you notice here in this first example, all the slopes are the same. In the second example, all the slopes are changing. Same with the third, but how they're changing is different. And if you notice, what happens is that when the slopes change steepnesses, it creates a bend in the curve. So a linear function has a constant slope. These two functions don't have constant slopes, and what's different about them is they have curvature. Now, if you remember from Math 2 and Math 4, the way we describe curvature in the function is the word concavity. So concavity describes the curvature of a function. Okay, and again, that's my little shortcut for function. Not all functions will have concavity. The linear function does not have concavity. Absolute value functions do not have concavity. There's no curvature. The integer function, if you remember our little step function, no concavity. The step stool function, no concavity, okay? It does not have to have concavity, but sometimes they do. Now, we're going to be able to describe a function based off its concavity. There are two types of concavity that a function can have. So two types. What we say is concave up, which I generally write as CCU, and you can write as concave up. You can write that on any test or quiz, and I'll totally accept that. Just know the AP exam does not accept CCU as anything. That's just like in Miss Bowman's class, we can use those shortcuts. So that's concave up. And the other one is concave down. Now, you might remember that from Math 4. I know Mr. Remus has some salad thing that he does with concavity. So if you had him last year, you probably talked about salad bowls filling up or spilling out. Okay. The definition for concave up, a function is concave up if the slopes are increasing. Okay. Or we could say y prime or f prime is increasing. Notice I didn't say positive, I said increasing. Okay, so let's look at what that might mean. Concave up functions are going to look like your parabolas. So notice that this example is concave up over its entire domain. And I like to call this like the smiley face, like concave up, you have a positive attitude, you're smiling. Concave down, you're frowning, okay? Now, notice here how I said that y prime is increasing. If you look at these slopes along this concave up function, some of these slopes are positive and some of these slopes are negative. But if I look at how the slope is changing, let's just estimate some slopes real fast. I'm going to estimate that one as a slope of 0. I'm going to estimate that one as a slope of 1. Now this point right here is steeper, so maybe that's a slope of 2. And this point is even steeper, so maybe that's a slope of 4. So reading the graph on the increasing interval is really easy to see that the slopes are increasing, and that's what's causing it to get steeper as it's increasing, which means it's concave up. Now on the negative side, if I look at this, let's say this is -1, -2, and -4 because the function is decreasing. You're like, Ms. Bowman, those slopes aren't increasing. Yes, they are. To go from -4 on the number line to -2 on the number line to -1, those values are getting less negative, okay? So if it gets less negative or more positive, then it is getting higher in value and is considered increasing. So notice I'm not saying the derivative is positive. I'm saying that the derivative or the slopes are increasing. So we could be decreasing with increasing slopes. And you're like, oh my God, what? So again, decreasing with slopes that are getting less negative. That's what increasing means. Okay, so concave down is going to be the opposite situation. So for concave down, your slopes, oh, here comes my pen, acting a fool. Slopes, or I'm going to say y prime, are decreasing. So notice now, we're not talking about what the function is doing. We're talking about what the slopes of the function are doing. So a concave down function would be like a frowny face. That function is concave down. And again, if I want to fill in these little slopes, that's a slope of 0. That looks like a slope of -1, -2, -3. That's a slope of like 1. That point has a slope of 2. Maybe we'll say that point has a slope of 3. So if I read this graph from left to right, the values of each slope, from a slope of 3 to a slope of 2 to a slope of 1, they're decreasing. They're getting less positive. Or if I keep going, it's still decreasing in value because it's getting more negative. So either it's going to get less steep on the positive on when it's increasing and steeper or more negative on the decreasing sides. Okay. So concavity describes how the, sorry, I just lost my whole train of thought. Concavity is this curvature, okay? And you get that curvature when your slopes are either increasing or decreasing. So what that means for us is when the derivative is increasing, the function will be concave up. So I can say if f prime increases, wow, come on, smart, my little surface. If f prime increases, I'm going to actually type this. Let's see. Ms. Bowman's going to try a hack, guys. Yeah, there we go. F prime increases, f of x is concave up. If f prime decreases, f of x is concave down. Okay. So now you're like, well, that's cool. But what does that mean with the second derivative? Well, let me ask you this. If I told you a function, no matter what that function is increasing, what could you tell me about their slopes? So if a function is increasing, no matter what that function is, you would describe their slopes or rates of change as positive. And if a function is decreasing, no matter what that function is, then those slopes would be considered negative. So to test for concavity, it's hard for us to see if like a derivative is positive or increasing or decreasing. But if the first derivative is a function, right, which is what we've decided in 3.2, that we can write derivative functions. Those functions, right, have slopes. So if a function, in this case, the first derivative is increasing, then its slope or second derivative would be positive. So to test for concavity, here's what we're going to say. Either if f of x is concave up, is concave up, there we go, then f double prime of x is positive. If f of x is concave down, that means f prime would be a decreasing function, which means its slopes, or f double prime, is negative. Okay. Now, if a function has no concavity, then the slopes aren't changing, which means the slopes rate of change is 0 and the second derivative would just be 0. Okay, now there are functions that look like this, like our little cubic chair. Okay, if I look at this function is increasing the whole time, which I can see, but the curvature is not the same. So if I look here, I have the first part of this graph looks like it's like a frown. It's frowning. It's getting less steep. And then it starts to get steeper over time. So we went from concave down. So this part is concave down to this part, which is concave up. So at some point, we had to change from concave down to concave up. This is called a point of inflection or an inflection point. So let's define inflection point because it has a tricky definition. A point where, oh, all right, it was working, guys, for like a hot minute, and then now it's lagging again. So what I'm going to do is just type this at the same time. I don't know why I don't do that more often. I just never think to. Okay, what did I say? A point where a function f of x changes from concave up to concave down to concave down. This is why I don't type. To concave down, or vice versa, is an inflection point. Now, what does that mean for the second derivative? This is where, so if my second derivative, let's think about this. If we went from concave down, that's a point where the second derivative is negative. If we change to concave up, now all of a sudden the second derivative is positive. So for an inflection point, this is where the second derivative, I'll say f double prime of x. Oh, I didn't even write the double. F double prime of x, or the second derivative, equals 0, and there is a sign change. The sign change is a necessary part of the second derivative for inflection points because in this example, okay, the second derivative at all of these points are 0, but there are not inflection points. So saying the second derivative is 0 just means there's no concavity at that instant. But to say that there's an inflection point, there needs to be a change in concavity. So the second derivative has to have a sign change. Okay, and that's a little like foreboding for what we're going to do. Today, we're just really focusing on like what do functions tell us about the second derivative and what do second derivatives tell us about the function. So we're going to go through an example. Here's your first one. For the functions below, what can be said about the second derivative? So I want you to pause me and say, what could I conclude about the second derivative of f, g, and h based on the graph and what I'm looking at for the graphs of f, g, and h? So go ahead and pause me, write down what you think you can say, and then unpause me and I'll go over the answer. So, okay, welcome back. Now that you've tried it. So if I look at f of x, I can see that we are concave up the whole time. Since f is concave up, what I can conclude is that f double prime of x is positive. And my justification would just be because f is concave up. So if I asked you, like, defend your answer, literally that's all you need to say. Now, I will tell me if you say it, the pronoun it, that is a no-no in my class, and AP exam will give you 0 points for using the word it, and I will give you 0 points for using the word it. Okay, so make sure that you're naming, because we could be talking about 3 different things. Use names throughout your sentences. Okay, second example, g of x. If I look at g of x, to be able to say something about the second derivative, I'm looking at concavity. So for g of x, I could say that g double prime of x is negative because g is concave down. Okay. Now, what could I say about g prime here? G prime of x would actually be positive. And I know g prime is positive because g is increasing. So we're going to be practicing this a little bit more next class, but just to kind of get you going on like here, what could I say? Now, if I look at h, H is an interesting case because over here I'm smiling, but over here I'm frowning. So I'm going to say, let's see, H double prime is less than 0 for X is less than 0. H double prime is greater than 0 for X is greater than 0. And I'm going to say H double prime of 0 is 0. Because at 0, there is a change from frowny to smiley. That would be an inflection point. And so I'm just going to put IP in parentheses. That second derivative's value would be 0 right there. Okay. Great work. So let's keep going. So now we're going to practice looking at the first derivative and the second derivative. So what I need you to do is pause me for a second and grab some colors. You need like 2 different colors to do this next activity. I mean, if you don't want to do it, that's fine because you're doing this asynchronously, but it'd be cool if you did. Okay, so grab 2 colored pencils, unpause me, and we're going to go through it. Whew. All right, so here we have a graph of f defined and continuous for all x. So we're just going to assume that there are arrows on the end since it says for all x. Okay, and we have this function here. So first, what I want you to do is color the graph where f prime is greater than 0 in one color and f prime is less than 0 in another, and then answer the question on what intervals is f prime of x positive. Okay, so think it over, try it. Pause me, unpause me. Okay, welcome back. So what I'm going to do is I'm going to color in purple everywhere where my first derivative is positive. So I have to think to myself, when it says the derivative is positive, what does that mean for our graph of f of x? Well, that means I have positive slopes. So I'm looking for where this graph has positive slopes. In other words, where is it increasing? So I'm going to color it to here, here, and then this whole section. And then for my second color, I'll do green. Okay, so negative slopes means that this function would be decreasing. And so to answer the question on what intervals is the derivative positive, well, it'll be anywhere our function was increasing. So I'm going to say negative infinity to negative 3, union negative 1 to 1, union 5 to infinity. Okay, now what I want you to do is now I want you to color this graph in one color where the second derivative is positive and in another color where the second derivative is negative. So go ahead and attempt it, and then we will go through it. All right, welcome back. Now, you might have struggled a little bit with this one, and that's okay because I'm going to tell you right now, we're just doing some estimations. It doesn't have to be like 100% accurate, and you'll get what I mean in a second. But if I'm looking for where the second derivative is positive, I need to ask myself the following. What does the second derivative determine about f of x? So in this case, where the slopes would be increasing is where the second derivative is positive. And how that would look visually is anytime my function is concave up or smiling. So if I look here, if I follow this function, I am concave down this entire interval, even past the hill. But then something happens in between here because now all of a sudden I'm kind of smiling. So there has to be a change. And I'm going to mark it right here. And this is where you may or may not, like it might be a little bit different than mine because we're just estimating and it's kind of hard to see the concavity. So I'm going to follow it close. I'm smiling, 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 smiling till about here. Probably where it looks the most linear is where it's going to change. Now I'm frowning, maybe to here. And then I'm smiling. And then I'm frowning. And then I'm smiling. And then if my second derivative is negative, that's going to be my frowning places. So now I have a nice colored graph and I can answer these questions. So let's answer these questions. What are the x values of the inflection points of f? Well, that's where my colors are going to meet. So negative 2, we'll say 0. I'm going to say 3.8. If you said 4, again, we're estimating it's not going to be 100% accurate. So just try your best. 6. And 7.5. Label the regions of graph CCU or CCD as appropriate. So CCD, CCU, CCD, CCU, CCD, CCU. There are some intervals where f prime is decreasing. What is the sign of f double prime in those intervals? So if my slope is decreasing, its rate of change would be negative. What is the concavity of f of those? It'd be concave down. And then it wants us to identify those. So I'm just going to say negative infinity to negative 2, union 0. I'm just going to call that 4. Union 6 to 7.5. Okay, so just a little practice using the second derivative to kind of help you. And now we're just going to do a couple more examples with the second derivative and then call it a day. So next one. Now we're going to interpret the second derivative as a rate of change in the context of a situation. So a population, I hope I fixed that on yours because this has been the same typo I've had for like 3 years. Remember how I said this is a judgment-free zone? We're not going to judge the fact that I haven't changed that typo. Hopefully I did, but maybe I haven't. Okay, a population P growing. If I haven't, guys, can you call me out? Because I'm, again, filming this in August, and I already made copies of your packets for the whole first semester. And if it's still in there, I really just need to fix it. So when we do this, please let me know if there is a typo still so I can actually change it for the first time ever. Okay, so a population P is growing in a confined environment. You might have seen this in bio if you've taken bio. The picture is shown below. What could you say about dp dt? And d squared p over dt squared. So remember, this is the same thing as p prime, and this is the same thing as p double prime. That's just the other notation so that you get used to using both. So pause me, think about this, and then kind of go through it. But if I'm looking at this, I'll give you a second. I'm going to take a breather. And I wanted to draw conclusions. I hope you've paused me and now you've unpaused me. Welcome back. Okay, here's my graph of P. What can I say about dp dt? Well, what I could say about dp dt is positive. And how do I know that? P is increasing the whole time. So since my function is increasing, since the population is growing, the rate of change of the population should be positive, okay? So no matter what the shape is, it is increasing in value the entire time. So we would say that dp dt is greater than 0 or is positive. I like to write it in inequality notation because it's faster, but if you're not comfortable with less than and greater than, just say is positive and you're good to go there, okay? Now for the second one, now it says, what could I say about the d squared p? So I'm going to say d squared p over dt squared. That's the second derivative. Okay, so what can I say about it? Well, if I look here, I have now, again, if I'm looking at the second derivative, my thought is CC. I'm looking for concavity. So here I am concave up. So I'm going to say positive for t's less than t0. We can say that it is then negative for t's greater than t0. And then I'm going to say that d squared p over dt squared, the second derivative, at t equals t0 is 0, because right here we have an inflection point. Point of inflection, inflection point. And remember, in that Leibniz notation, it's a little bit different than function notation. Okay, you don't put parentheses in t0. You're going to draw a line and write that. I know you're going to get used to it. We're going to go back and forth between both, just so you're comfortable with both notations over time. Okay. All right, let's look at another one. 2 more. Whew. So estimate the rate of change for 3 to 6, interpret its meaning. Okay, so let's see here. The table below shows the results of testing the C5 Chevy Corvette. Use the table to answer the following questions. So we have this table. We want to, oh, they're throwing us a curveball. This is an example of your very first free response problem that you could see. So welcome to calculus. We're doing an actual free response, part A, part B, part C type of problem. We're going to talk more about the AP exam as we go through, and I'll be kind of mentioning it as we go, but you will, if it's in person and not online, you will have 6 free response questions, and one of them is always a table. Okay, so estimate the average rate of change from 3 to 6, interpret its meaning, use the table to estimate v prime of 7.5, and then what could you say about the sign of d squared v over dt squared over the interval 0 to 12. So take a moment and pause me and answer these questions, okay? And then unpause me. Now, if you're really like, I have no idea, that's okay. You don't have to pause me. But I would love it if you did and tried it, and then we'll go through. Okay, so average rate of change. If I want the average rate of change from 3 to 6, That's the slope. So I would do 33 minus 20 over 6 minus 3, which gives me 13 over 3. Now I need to think about my units. 33 and 20 were measured in meters per second, so it'd be meters per second over seconds, so meters per second, or you can write that as meters per second squared. So what does that mean? So that means from 3 to 6 seconds, the velocity, because that's what our table is, that's the function they're giving us, is increasing at 13 over 3 meters per second squared. Okay. Use the table to estimate v prime. Now, here is a key part from this example that I want to make sure you walk away with. It's asking me for the derivative. All I have are 5 points on this table, guys. There is no way I can do a limit. So if it asks you for a derivative, you know that's the IROC. In order to find an IROC, you would need to have a graph or an algebraic expression. We have neither here. We have a table. So the only way what we can do is estimate the IROC. So that's why it's using the words estimate. So if we want to estimate the IROC at 7.5, I'm going to look. 7.5 would be between 6 and 9. So I'm going to use the AROC to estimate the IROC. And that's legal because if you remember our local linearity conversation, if I zoom into a function, like the points right around it are going to be pretty similar to it. So if it's, as long as it's differentiable, then we're fine there. So we're just going to take the slope between 9 and 6. So 43 minus 33 over 9 minus 6 gives me 10 over 3 meters per second squared. Okay, last question. What could you say about the sine of d squared v? Now, I got to think to myself, I have a velocity, and it's asking me about the second derivative, which means it's asking me about the concavity. I can't tell what the concavity is of this graph based off what I see here. So I'm going to think about what else the second derivative tells me. So it tells me if the function is concave up or concave down, but it also tells me if the first derivative is increasing or decreasing. So if I look at the slopes of these points, we go from 20 over 3 to 13 over 3 to 10 over 3 to 3 over 8. So if I look at these slopes, oh wait, I just did that, 8 over 3. Oh, I just did that backwards. If I look at the slopes, the second derivative describes how the slopes are changing. So if I go from 20 thirds to 13 thirds to 10 thirds to 8 thirds, I can see that those slopes are getting smaller. My slopes are decreasing. Therefore, I can say that d squared p over dt squared is negative because the slopes, which would be dv dt, are decreasing. So dv dt is decreasing. So since the slopes are decreasing, the second derivative is negative. Wow, that just didn't even look like, that doesn't even look like language. Okay, is decreasing. Okay, last example. So speaking of this example, before I move on, this is measuring velocity, and that is something that we're going to talk over and over and over again. One of the biggest applications of calculus exists in physics, and if you're currently taking physics, you are going to do these problems a lot from the physics perspective. So position, velocity, and acceleration are kind of 3 levels of functions that we talk about in the physics world. Okay, now position usually measures a distance, velocity is speed plus direction, and acceleration describes how your velocity is changing. So if we're talking about position, velocity, acceleration, that's also talking about like function, first derivative, second derivative. Okay, so position, velocity describes position, acceleration describes velocity. So it's kind of like f prime, f double prime in our world, and we're going to be practicing these a lot. So I kind of wanted to throw one at you and see what you can do with it. This is guaranteed to be a free response question if we're at normal times in May. Okay, it's been a free response question every year except for last year, but we don't count last year. So let's go through this one. A particle is moving along a straight line. Its acceleration is 0 only once. So that's your clue. Second derivative. Its distance s to the right of the fixed point is given by the figure. Estimate a when the particle is moving right and moving left, and b when the acceleration of the particle is 0, when it's negative, and when it's positive. So again, if this is our function s's position, then velocity would be s prime and acceleration would be s double prime. Okay, so if I want to know when my function is moving to the right and moving to the left, looking at this, if this is my function's distance, I can see here at time 0, it's at a distance of 0. And then by time 0.6, we're at a distance further away from 0. So here I can see that my distance is increasing. And then my distance is decreasing. And then my distance is increasing. So we're going to be moving right anytime where the distance is increasing, and moving left anytime where the difference is decreasing. So we're going to move left, we'll say, or we'll do right first. So right would be 0 to 2/3. And then from 2 to infinity. And then it's moving left anytime we're decreasing. So that would be from 2/3 to 2. Okay, part B. When is the acceleration of the particle 0? So again, acceleration is the second derivative. So the second derivative is 0 at an inflection point, which would be right here at 1 1/3. So I know the acceleration, which we'll say s double prime of 1, we'll say 4/3 is 0 because we have an inflection point, and I'm just going to put IP for the sake of time. Okay, a lot of times we'll use A for acceleration too. So you could just say A of 4/3 is 0. Okay, and then where I want to know where A of t is positive and A of t is negative, or acceleration is positive, acceleration is negative, where the graph is CCU and CCD. So it's CCU from 4/3 to infinity. And it is concave down, those are supposed to be arrows, from 0 to 4/3. Okay. And those are parentheses because at 4/3, the acceleration is actually not greater than 0. It is 0. At 0, if you want to include 0, you can because it's an endpoint, but I won't take off either way. Okay, guys, well, that was day 4. So great job, and I will see you soon.